reduced form. So there is no such unique canonical expression in a free Q group. However, still there is a way to work with free Q group, and this was also described by Baumschlag. So I will present this description in the case when X is a countable set. So the Baumschlag showed that there is a collection of subgroups of FQX such that the first subgroup is a free group on X. Then the union of these subgroups give us the whole group, and the GI plus 1 is obtained from GI by adding a root of a generator of maximal abelian subgroup in GI. So we add roots, and eventually we will construct any element in a free Q group. Okay, the question that I want to consider, this is a conjecture of Baumschlag. So I think he proposed it in 60s, 68 maybe. So the conjecture says the following: the free Q group is residually torsion-free nilpotent. So residually torsion-free nilpotent means that for any non-trivial element of G, we have an homomorphism to torsion-free nilpotent group such that the image of this element is not trivial. One of the motivations for this conjecture is a result of Magnus. Let me recall this result of Magnus. Let's fix a set I and fix two sets indexed by this set I, X and Y. So we can consider the ring of non-commutative power series over Y. And the Magnus showed that a free group can be embedded as a multiplicative group of this ring. And the embedding is the following. You send a free generator Xi to the power series, or the polynomial in this case, 1 plus Yi. Okay, because since this group is a Q group, so this map is can be uniquely extended to a map from free Q group to the same multiplicative subgroup of the ring of non-commutative power series. And now, this was maybe the main motivation of Baumschlag. He observed that, in fact, in order to show residually torsion-free nilpotent, it's the same as to show that this map is injective. So the Magnus map is injective when we apply it to free Q group. Another observation that we can make from this result is that in order to show that free Q group is residually torsion-free nilpotent, it is enough to consider only its finitely generated subgroups. So this is a local property. And in this way, we can reformulate the Baumschlag problem. So using this description that I gave before, so we now can reformulate the Baumschlag problem as the following. Assume we have a collection of groups, G0, G1, Gk, such that G0 is a free group, finitely generated free group, and Gi plus 1 is obtained from Gi by adding a root of some generator of a maximal abelian subgroup. So in this case, in this formulation, the conjecture says that Gk is residually torsion-free nilpotent. So the case k equals 0, so when G0 is free. So this is Magnus. And Baumschlag himself proved the case K equal 1. So the case when you extract one root of some non-polar element in a free group. So the main result of this talk is the following result. So here's the situation. Is slightly more general. So we have a collection of groups, a sequence of groups, such that we start again from a finitely generated free group, and then we add, we construct the next term, we construct as an amalgamated product. So amalgamated product of the previous group, Gi, with a torsion-free finitely generated abelian group over a maximal abelian subgroup of Gi. So in the previous situation, all Bi aside. So in Baumschlag conjecture. So this corresponds to the case when all Bi aside. So here we allows also Bi to be Z to the K. So in this situation, take a prime P such that there is no P torsion in this quotient. So because there are these groups are finitely generated, it's a finite family of finitely generated abelian groups. So this condition holds for almost all primes. So let's take such a prime, then and consider free propy group, which is the propy completion of F. Then theorem says that the embedding, so natural embedding that we have at the beginning, yeah, so G0 is F, can be extended to an embedding of GK. So, okay, the proof will be by induction. So you first extend G1, then G2, G3, and finally you extend it to GK. Okay, F is a free propy group. It's the propy completion of free group. It's a free propy group. And it's well-known fact that it is a residually torsion-free nilpotent. In particular, theorem A gives us the Baumschlag conjecture. Okay, so now I would like to explain the ideas of the proof. If there is any question so far on the notation, maybe about Q groups. Okay, let's go to the proof. So I will use some ring theory ideas. So let me fix first the notation. So as before, G will be a group, K is a commutative ring. Normally it will be a field. Kg is the group algebra. IKG is the augmentation ideal. So we have a map from Kg to K, and the kernel of the map is the augmentation ideal. For any subgroup H, I will consider the following left ideal of Kg. So I take this is KH. I take the augmentation ideal of KH and generate with its elements the left ideal in KJ. So all my models are left models. So if you want to understand this as a left model, it's isomorphic to this tensor product. So the general problem then, okay, of course, very often, because it's too general, but yeah, is the following. Assume we have a group, which I denote by G tilde, which is given by generators and relations. And we have a nice group. This is nice group, G bolt, for example, SLN or propy completion of G tilde or propy completion of G tilde, or profinite completion of G tilde. So we have some nice homomorphism to some nice group. And we want to show that this map is an embedding. So, okay, I will propose a way to attack this problem. And first observation then is the following, this is theorem B, is the following, that we can understand a part of the kernel. Okay, we can understand the abilization of the kernel using the following result. So assume that so we have this map. So this is the augmentation ideal of G. And of course, we have a map. This is augmentation ideal of G tilde. So we can map. So this is element of KG. We have this element of KG tilde. We can send it to element of KG in the natural way. And assume this map is isomorphism. Then it implies that the abilization of the kernel is okay. This part, okay, depending on characteristic of K, or torsion-free if characteristic of K is 0, or P part if the characteristic of K is P. This part of abilization is trivial. So, of course, this is only partial information about the kernel, but sometimes we know that kernel is, for example, free, and this will be the situation in my arguments. So the kernel is free. So this will be already enough to show that the kernel is trivial. So if plus kernel is free implies it's trivial. So I would like to use this idea, and okay, in order to use this idea, again we have this situation. Also we have a group given by presentation. So we have this map, and G is the image of this map, and we want to show that K is trivial. So as the first step, we want to analyze this application. So this application of KG models. And we want to show that this application, this map is isomorphism. And the idea how to show that this map is isomorphism is the following. Assume we embed the group ring in some division ring D. Yeah. And okay, this is MN, is you can think about it like MN. Assume we have this surjective map of KG models. And we have two additional conditions that the D dimension, so when we extend the scalars, so the D dimension are equal, is the first condition. And the second condition is that this model M is D torsion free. So D torsion free means that it's submodel of D model. So the proposition says that in this case we have isomorphism. So okay, this is trivial observation, but you can think about abelian groups. So abelian groups are Z models. So if you have two abelian groups, A, B, so that Z models. So assume that this dimension I equal. So in this case, Z can be embedded in rational numbers. So this is like Z, this is like rational numbers. So I assume that Q dimensions here are the same. Yeah. And assume also that R is torsion free. So, okay, you see, of course, that this implies that, so this is on the map. So it implies that, of course, there is no kernel. No, because if there is a kernel, it will somehow, it will contradict to this. And basically, this is the same idea. It's the same proof. Yeah. So, but it gives us a way to analyze this map, yeah, and attack the problem. So, resuming, our strategy will be the following. So, we have this situation. We have a map from G tilde to some nice group G ball. Then we have G is the image, and we want to show that the kernel of this map is trivial. So first, what we want to do is to find a nice embedding of KG in division ring. Then we want to calculate this dimension. Okay, this also can be expressed as the dimension of the first homology group plus 1. Second, we want to calculate the second dimension. So this is what we have here in this theorem B. So this is two models which appears in theorem B. So, and this is what we have here. We calculate their dimension. Now, assuming that they're equal, yeah. Now, the first step is to show that this model is torsion-free. Now, together, theorem B gives us, implies that if these two numbers are equal, and this is torsion-free, implies that K is 0. No. So this part of abilization is trivial. And now we finish the proof, for example, finish the proof that K is equal to 1, for example, by showing that K is free. Okay. So this is our strategy. Okay, so now let me start with the point 1, step 1. What kind of embeddings do we know? So what are the candidates for KG for the embeddings of group algebra in a division ring? In fact, there is a very well-known problem that says the following. So assume we have a group G and a field K, and assume also that we know that KG is a domain. Then KG can be embedded into a division ring. A particular case of this problem is known as Maltsev embedding problem. Maltsev embedding problem. So this problem is for G is left orderable. So when you have left orderable group, I think it was Higman. So in this case, KG is a domain. So, and the Maltsev asks whether for left orderable group, you can embed KG in some division ring D. So this is known as Maltsev embedding problem. So Maltsev and Newman proved it for the case G is B-orderable. So there is the famous construction of Maltsev-Newman Power series, and this gives you embedding of group algebra of a B-orderable group to a division ring. In the case of characteristic 0, there is another conjecture which is much stronger, in fact, than the previous one, and this is Atiyah conjecture. So original Atiyah conjecture for torsion-free groups can be stated as the following, that all L2 Betti numbers of free co-compact GCW complexes are integer numbers. So I will not explain what are L2 Betti numbers, but what I need is that for us, it's important that this is equivalent to the following statement that some ring, which you can define ring, linear ring, it's defined inside of ring of affiliated operators, UG. So I will not explain what is this. So some ring which contains QG is a division ring. Yeah. So Atiyah conjecture implies much more that we say here, but okay, it's in this case for Q, but in fact there is a version of Atiyah conjecture for arbitrary field of a characteristic 0. So it implies that in fact that if you start with torsion-free group, then QG can be embedded in division ring. In fact, it also implies Kaplansky conjecture that QG is a domain. So it's Atiyah conjecture. It's a strong version of Maltsev embedding conjecture for in characteristic 0. So this is known for many groups, and for example, we proved it with Diego Lopez for locally indicable groups. So it gives us a lot of examples when we can somehow start this strategy. So it gives us a lot of examples of nice embedding of KG in a division ring. However, I will not use this in my talk, or I don't use it in my proof. So the point is that there is, I need a characteristic P version of this result. So there is a point, I will explain it later, there is a point on the proof that I cannot prove in characteristic 0, but yes, I can in characteristic P. But the characteristic P analog of Atiyah conjecture, or all these conjectures, is much more complicated. So the situation is much more complicated, and there are less examples of embeddings. So the embedding that I will use is the following. So here where free propy group appears. So in this case, so if I start with free propy group F, so when we work with propy groups, we can consider completed group algebra. So okay, I will give the definition. Maybe it's not very important for this talk, but just so completed group algebra. This is this inverse limit when n is the open normal subgroup of F. So it's an analog of group algebra, but in the category of pro-P groups or profinite groups. But it's not important, the definition. What is important for us that if you have a free pro-P group, then its completed free, its completed group algebra is isomorphic to very easy ring, okay, ring that we understand. It's the ring of non-commutative polar series over FP. So the isomorphism is the following. So if you have F is given as x1 xd, okay, as propy group. So you have this map. And the map sends xi to 1 plus ti. And this is isomorphism. This is isomorphism. Okay, so this ring, of course, we understand it very well. And in particular, we know that this ring has universal division ring on fractions. Okay, I will not explain the notion of universal. So this is notion of universal. So it was proved, I think, by Kohn also in 60s. So what is important that we have some nice division ring where we can embed this ring. And in particular, what I need that this is isomorphic to this, I can embed it. Okay, this is this ring. So I have a very nice embedding of my completed group algebra to some division ring. And now when I have a group G subgroup, discrete subgroup, not profinite, discrete subgroup of F, so I can embed FPG to division ring. And this will be the embedding that I will use in this paper. in this talk. Okay. So it gives us the first step. So we okay, as you say, K will be in our case will be FP, G in our case will be this G both will be free group, free pro P group, and the embedding. So we will embed FPG. We will embed with this ring division ring that I explained the existence that exists for power for the ring of power series. Okay, now we need the second step. So the second step, it's in fact it's quite easy. We will see it during the proof. But basically, what you have in the second step, you have augmentation ideal of G tilde, and you want to calculate this dimension. But since we have a representation for G tilde, it's quite easy to write down also relations, generators, a relation of the augmentation ideal, and from this it's quite easy, normally quite easy to calculate this dimension. So it will be easy step. There is no problem here. So let's speak about the third step. So this is a bit more involved. So now what we have a group G, and only what we know about G is that this group is, okay, in this case, that this group lives in this free propy group F. So we want to use this information in order to obtain information about this dimension. And this is the context of theorem C. So, okay, so now we have this embedding, and now we can calculate the theorem Three gives us an estimate for this dimension of this cohomology group. Okay, you can think about it as a mod P analog of the first L2 bit number. In fact, I call it this number. I call it like the first mod P L2 bit number. You now will see the motivation, but this is really the analog, mod P analog of mod P L2 bit number. So in order to prove this, I will need another result, and this result is analog of look approximation. So what is the look approximation? Let me recall look approximation and then state the result, which will imply theorem C. So look approximation is, I will give okay version which I need for this talk. So if we have a finitely presented group and we have a chain of normal subgroups of G of finite index with trivial intersection, so Luke proved that there exists the limit of these normalized Betti numbers, and this limit is first L2 Betti number of G. So sometimes, okay, if you want to apply this for arbitrary group, you really need to ask, you need this condition, finite representability. But in some situations, for example, if the group is residually torsion-free nilpotent, residually torsion-free nilpotent. So in some situation like this, really it's also this formula holds for finitely generated groups. And the following theorem is a mod P analog of this result. So, but in mod P situation, there is no full analogy for it. So it's conjecturally, of course, we have this as a conjecture, but there is no theorem which gives us a full analogy of look approximation in characteristic P. So this is one very small instance of look approximation in characteristic P. So the theorem says the following: assume you have a finitely generated subgroup of a free propy group. We fix a chain of open normal subgroups with trivial intersection of F. This gives us a chain of in G. And for this chain, this analog holds. Yeah, and what is important here, we only assume finitely generated. Okay, like here, like in this case. Yeah. So, okay, a few comments about mod P look approximation. So, for example, it's known for amenable groups, but if the group is not amenable, I would say that almost nothing is known. So this is a very rare result when you have something positive. So it's very open at this moment. Okay, I will not explain the proof of this, but I will show how this theorem D gives us the bound which we need in the step 3. So now we have the following situation. Assume we have a dense subgroup of free propy group F of rank D. And in this case, we can calculate, okay, or at least estimate this, as I said, this is a mod, the mod PL2, the first mod PL2 Betty number. So the proof is the following. Okay, we fixed this chain of open normal subgroups of F with trivial intersection. We consider the corresponding chain in G. Now we consider this the Betty number with coefficients in FP. Okay, this is equal to this number, and because G is dense, so G is dense, we have here inequality. So G is dense in F. We have inequality. Now this number, we know this value because F is 3. So this is Schreier formula. F is a free propy group. So we have Schreier formula. And now again, G is dense. These two indices are the same. And we obtain this inequality. And now using theorem D, which says that this number is the limit of normalized first Betty numbers of GI, we obtain the inequality that we wanted. So theorem Three is a consequence of mod P look approximation. So until now, you can do everything in characteristic 0, because really in characteristic 0, theorem Phi is for free, because you have look approximation. So the same proof works, and using look approximation, analog in characteristic 0 is obtained in the same way. Yeah. But the next step, so in the next step, so this was the step 3. Now the next step is to show that some model is torsion free. And in this step is where we really need characteristic P, at least at this point. So the next step says that this model, which is the following model, so start with a dense subgroup of, dense subgroup, finitely generated subgroup of free propy group F. Take a maximal abelian subgroup of H and consider this model. So this is FPH model. So FPH we embed in DF. And the theorem says that this model is DF free. So the characteristic 0 analog of this result that I believe should be true, but just I don't know how to prove it, it's the following. So if you take if QH is okay, in this case the analog is, this is linear linear ring of fractions. Is D torsion free. So I believe that also in characteristic 0, we have this result. So this model is DH torsion free, where DH is the linear ring of fractions of QH. But I don't know how to prove. So here really we use characteristic P, and there are some things that help us because we work with FP, not with Q. As a corollary, we obtain that this model, okay, this model is DF torsion free, and this model I will use in my proof of theorem A. So this, the model is the following. So you have in this situation we have a finitely generated subgroup of F. We have another abelian subgroup of F, abelian subgroups in such that the intersection of H and B is maximal in H. And so in this case, this model is DF torsion free. Okay, so basically, so we have all 5 steps, and now we are ready to apply this and to prove theorem A. Theorem A will be proved by induction, so I really need some inductive step. And in order to define this inductive step, I need some technical definition. So this is definition of a strongly embeddable group, subgroup. So what is a strongly embeddable? If you recall the theorem C, yeah, it says that when we have a dense subgroup of free proper group of rank D, we have this inequality. So the condition to be strongly embeddable is that G is dense, but you have also equality. You have strict equality. So this is a condition that I need. And okay, the obvious example is a free group. Free group, when it's embedded in its proper completion, so this is its proper completion, is strongly embeddable. So this okay, this is immediate calculation. And so now we have this theorem F, which is inductive step in the proof of theorem A. So it says the following: assume we have this SE subgroup, strongly embeddable subgroup of free proper group of rank D. Assume also we have a finitely generated abelian subgroup of F with the condition that when you intersect it with H, you have a maximal abelian subgroup in H. Yeah. Then okay, we can generate H, a group with H and B, and we have a natural map from this amalgamated product to the subgroup of F generated by H and B. And so the theorem says that in fact this is isomorphism, and moreover, okay, this we need also for inductive step that this group is strongly embeddable. So we use the previous notation. This will be our G tilde. This is the image in F, G, and K is the kernel of phi. So the step one is the embedding. So we have the embedding of FPG. We have embedding. We produce it embedding to the DF. So this is step one. Now, because we know G tilde very well, as I said, we know what is the augmentation ideal. So this is okay, FP. This augmentation ideal of FPG tilde. So this was proved by Swan in 1969. And from this, it's almost immediate is a calculation of this kind of dimension. So, okay. So when we tensor, basically, the point is that dimension of with E with G tilde is 1. This dimension is 1. is 1 because B is abelian. B is abelian, so it's not difficult to see the 1, and the same is for A, and basically it's you obtain the same dimension as of H, which is D, because we have the condition that H is strongly embedded. Yeah, now the theorem C gives us 3. So theorem 3 gives us that is greater, is at least D, but in fact it cannot be greater than D because this dimension is at least this dimension. So the model that we consider here is a quotient. So again, this model is a quotient of this model. So this implies that we have in fact equality here. So we have D in both cases. Now theorem corollary for E gives us that this model, which is exactly which appears in corollary E, is dF torsion free. And so what we have from 1, 2, 3, and 4, we have that the kernel, the P part of the kernel is trivial. Yeah, but now, okay, this group G tilde is an amalgamated product, and A is a subgroup of G. When we look this phi on this map restricted on A is injective, it means that A does not intersect with the kernel, and okay, Basser theory gives us that K is free, and now this means that K is 1. And theorem A is induction. It's induction. So you will have, again, recall that in theorem A, we have a collection of subgroups. So such that the first subgroup, collection of groups, the first group is F, free group. And then we obtain the next term of the sequence by adding a root of this is by amalgam, and we obtain the next term by amalgamating of a maximal abelian subgroup of Gi, and Bi is a torsion-free finitely generated abelian group. So we have this prime such that it does not divide this. The torsion. There is no torsion in this abelian group, and we want to show that, okay, by induction we will want to show that Gi can be embedded in F. So the base of induction is clear. So in this case we have a free group is already in F. So now we assume that everything holds for I, and we try to put it for I plus 1. Yeah, we put Gi is H, A is AI, and B is Bi, and we now observe that we can extend this embedding to embedding of B. So we have A, it's in F, we have here B, and there is no P torsion. There is no P torsion here. And this means that we can embed. And normally there is no unique embedding, but it's unique. This extension is unique if and only if B over A is finite. But in general, you can have several extensions. And now this means that we can think about B as a subgroup of F, H is a subgroup of F, and now we are in the situation of theorem F, which gives us an embedding of Gi plus 1 into F. And this finish the proof. Okay. So I hope that it will be more applications. So at this moment we have another application but this is somehow it's obvious extension because it's also use free propy group. So this application is for para-free groups. So para-free group is a group which is residually nilpotent, and for every n, this quotient by the nth term of low central series is the same as the quotient of f by its nth term of low central series, where f is free group. So this is the definition of para-free group, and also this notion was introduced by Baumschlag, I think, also around 68. So para-free groups has a property that it's propy completion. Again, it's a free propy group, and in fact they are residually p. So they are subgroups of free propy group. So all this, what I explained before, it's somehow it's naturally applied also for para-free groups. And so in our result with Ismail and Morales, we described the amalgamated products and I-chain extensions over cyclic groups. We extended para-free amalgamated products and I-chain extensions over cyclic groups. So we gave conditions, if and only if conditions, when amalgamated product of a cyclic group is para-free, or when I-chain extension of a cyclic group is para-free. So for example, in the case of amalgamated free product, so it's para-free if and only if we have the following three conditions. So the conditions that U and V, the groups which amalgamate, should be para-free. Okay, there is natural condition on this element, V to the -1 as an element of this product, and there is another natural conditions, and one of these two elements is not a proper power and the corresponding group. And in the case of I-chain extension, okay, this is a bit more complicated case. In fact, it's more complicated. There is a similar three condition, but we need the fourth condition. So it's also necessary, and this condition is unfortunately it's condition for W. So we need a condition that U is not trivial in some nilpotent quotient of W. So implies, and again, this is if and only if conditions. Okay, let's put some questions or problems. So my main motivation when I started to work on this project was to understand subgroups, abstract subgroups of free propy groups. So basically what the method shows that you can prove is that free ZP group, where ZP is free ZP is ring of p-adic numbers, can be embedded in free propy group. So this group is defined in the same way. So we defined it Q groups, but okay, you can define A group for a ring, commutative ring A. So the natural question, can you construct other groups? So really, this will be nice to construct more examples. And the motivation for this is the question of Lubotsky, which asked whether free propy group is linear over field. And in fact, we don't know whether free propy group can be embedded in SL2C. So this basic question we don't know. And of course, what my result shows that this problem of Lubotsky is related with another known problem on Q groups, which was posed by Ilya Kopovich, which asked whether free Q groups a linear overfield. So of course, now these two questions are related, and somehow any programs on one of them will give okay, some partial result to nothing. Okay, this was what I wanted to say today. Thank you.
Thanks, Andrei. Any questions?
So Alexei here. Nice talk, Andrei. It might be a little bit far, but suppose you have not a free group starting with, but free solvable group. Say free metabelian even.
Yeah.
So you can get Q completion of this group because the group is residually torsion-free nilpotent. Then Q completion exists, and it's G embeds into G to the Q. Looking at the steps you had, 1, 2, 3, 4, some of them it seems like will work for soluble groups. For example, the algebra, group algebra will be, it has a field of fraction, division ring of fractions.
Yeah.
So you mean free solvable, right, Alexei?
Yeah, free solvable, but yeah. I'm not sure about the induction step because it somehow looks really much more complicated. You need Sven results and so on. But I don't know. Is it really far from what you are doing?
Really, I don't know. I have not thought about it. So really, I have to think about it somehow. Yeah.
That was another problem that Baumschlag, Gilbert Baumschlag was also interested.
So the problem is whether these groups are torsion-free.
Yeah.
Residually torsion-free nilpotent.
Yeah. There is no precise analog of Magnus embedding, but yeah, there is a, not in power series, for example, Magnus embedding into the modules for free metabelian C groups, but yeah, it's an interesting question.
So Alexei, wait a minute. So basically, for example, the question is take a free metabelian Q group, right?
Yeah.
It's torsion-free nilpotent.
Residually torsion-free
nilpotent. No, I mean, yes, whether it's residually torsion-free nilpotent.
That's interesting for various reasons. There are some applications, but it's interesting because it might be the same strategy might work, I think. Similar strategy, I know.